Active airspace is a chaotic environment. Every second, sensors log commercial flights, weather patterns, military activity, and random environmental noise. When an unidentified object appears in this environment, the historical approach has been to look back at whatever data happened to be recorded. This episodic, retroactive analysis almost always fails because the collected data is poorly calibrated, heterogeneous, and incomplete. To study unidentified anomalous phenomena scientifically, we have to define what a UAP actually is. A UAP designation is an epistemic state. It means the evidence available is simply insufficient to determine the object's origin. It is not an assumption of non-human technology. Establishing scientific resolution requires a transition to sequential experimental design, using real-time sensor tasking to capture calibrated data as an event unfolds. This flowchart details the PTCP TNQG SARAHAI architecture. The pipeline begins up the sensing and calibration layers, ingesting multimodal telemetry. It moves through predictive filtering and geometric inference layers, finally outputting an auditable, human-readable case file. By maintaining an active predictive tracking framework, the system captures transient, ambiguous sightings and systematically forces them through a mathematical filter until they yield actionable scientific data. The system relies on a continuous feed of physical inputs, including radar cross-sections, electro-optical and infrared imagery, weather conditions, and local infrastructure telemetry. For every observed object, the architecture builds a latent physical state vector. This tracks physical kinematics, like position and velocity, alongside spectral signatures and optical morphology. To identify a true anomaly, the system must first map normal behavior. It establishes a pattern of life baseline consisting of prosaic objects like migrating birds, commercial flights, and weather artifacts. This baseline is constructed by the Predictive Tensor Control Plane, or PTCP. The PTCP continuously ingests high-dimensional telemetry to model this massive environmental dataset. Because active airspace probability is computationally overwhelming, the PTCP uses tensor train decomposition. It compresses high-dimensional data into linked cores for rapid edge evaluation. When an event occurs, it calculates a raw anomaly score, determining how mathematically improbable the state is against the baseline. Relying solely on this raw score is a vulnerability. Broken sensors, corrupted metadata, or lens flares are highly improbable events, and they will easily trigger a high anomaly score. This equation shows the evidence-adjusted anomaly score. To prevent false positives, the system applies strict penalty terms. It heavily penalizes missing metadata, cross-sensor contradictions, and low track quality. The PTCP acts as a mathematical filter. It aggressively screens out sensor artifacts and poor data long before they can be mistakenly escalated as extraordinary physical events. If a tracked object successfully bypasses the baseline model without triggering data quality penalties, the system must gather more information to resolve it. This diagram illustrates the information geometric view of UAP resolution. Using Tensor-Network Quantum Gravity as a computational framework, it maps objects, sensors, and hypotheses as graph vertices. Evidentiary relationships form the connecting edges. The dividing line represents a minimal cut within the geometry. The minimal cut mathematically identifies the exact piece of missing evidence needed to pull a track from an unresolved status into a known prosaic explanation. To acquire that missing evidence, the system calculates expected information gain. This formula strictly weighs the value of a potential action against its operational cost or risk. Based on this calculation, the system physically retasks its sensors in real time to capture the specific data that will maximize ambiguity reduction. If an optical signature looks anomalous, the system might task a multisensor gimbal to collect a thermal background frame to rule out glare. Or, if a bright light appears at a specific altitude, it might automatically query catalog ephemeris data to confirm a satellite flare. TNQG identifies specific information bottlenecks and directs the physical acquisition of missing evidence, resolving ambiguity through targeted observation. Overseeing this active loop is SARAHAI, the system's semantic, explanatory, and human interface layer. This flowchart displays the anticipate, observe, track, understand, and engage loop SARAHAI manages. It maintains an auditable evidence graph, keeping hypotheses separate. To interact safely, it enforces a safety envelope. A quarantined challenger model learns baselines, while the live champion model executes real-world tasking. The system is restricted to observing, preserving captured data, and deconflicting airspace. Autonomous kinetic actions are entirely prohibited. Because the architecture separates scientific uncertainty from operational sensitivity, it can be deployed discreetly to monitor critical infrastructure or sensitive airspace without broadcasting classified capabilities. SARAHAI ensures that the complex tensor mathematics remain chained to rigorous human oversight, resulting in falsifiable hypotheses and scientifically controlled case files. The ultimate product of the PTCP, TNQG, and SARAHAI pipeline is a robust, peer-review-ready case file. This is the peer review evidence ladder, a standardized protocol classifying UAP claims based strictly on data quality. The default path for any observation is aggressive de-escalation toward the lowest rungs, level 0 for artifacts and level 1 for prosaic objects. Escalating an event to level 3, an unresolved multimodal track, or level 4, anomalous kinematics, requires reproducible, calibrated evidence that explicitly rules out prosaic confounders. A high anomaly score alone is insufficient. The highest tiers, level 5 for an agency hypothesis and level 6 for a communication hypothesis, are only considered after ordinary explanations are exhausted. These levels apply physical tracking logic to stimulus-response patterns. Level 6 is a rigorous statistical test. If the system emits a pre-registered signal, it measures if the object's subsequent behavior shows a mathematical dependency, framing interaction as a quantifiable relationship. Historical UAP research has long been hindered by the reliance on isolated post-hoc imagery. This architecture replaces that uncertainty with multimodal rigor. The PTCP compresses the baseline airspace model. TNQG identifies the geometric bottlenecks where evidence is missing. And SARAHAI manages the real-world execution while translating the resulting scientific certainty. Together, they allow all of this chaotic, ambiguous sensor data to instantly collapse into a singular, highly calibrated, and rigorously peer-reviewed scientific resolution. True UAP science requires abandoning the retroactive question, "What was that?" in favor of asking exactly what data must be collected right now to strip the phenomenon